Hey kiddos, welcome back. We've now finished talking about how to write formulas and name ionic compounds. Now let's talk about a few properties of ionic compounds. First of all, an ionic compound that conducts an electric current when dissolved in water is called an electrolyte. So if you can imagine sodium chloride being dissolved in water, it can conduct an electric current. Now we're going to learn more about these later in the year. For right now, you just need to know when an ionic compound dissolves in water and conducts electricity, it's called an electrolyte. The second thing, because ionic bonds are relatively strong, the crystals require large amounts of energy to be broken apart. That means ionic compounds have high melting and boiling points. It's hard to melt and boil them. They take a lot of energy to break them apart. So they have, once again, high melting and high boiling points. And then third, the strength of the ionic bond, something called the lattice energy, is directly related to the charge of the ions and inversely proportional to the size of the ions. Now what does that mean? That simply means directly related to the charge. As the charge of the ions get bigger, the lattice energy gets stronger. And inversely proportional to the size means as the size gets smaller, the lattice energy gets bigger. It's harder to break them apart. Thus, magnesium oxide would have a higher lattice energy than sodium chloride for two reasons. First of all, remember magnesium forms a 2+ ion and oxide forms a 2- ion. So we have a higher charge, and remember the lattice energy is directly related to the charge than sodium and chloride, which only have a 1 positive and 1 negative. Magnesium ions and oxide ions are much smaller in radius than both sodium and chloride. So remember, if they're smaller, the size is inversely proportional to the lattice energy. So, as a result, the melting and boiling points of MgO would be much greater than NaCl. It takes more energy to melt magnesium oxide and boil magnesium oxide than it would sodium chloride. Let me give you a couple more examples. Take a look at this table on the next page of your notes. Let's look at potassium iodide and its lattice energy. 632 kilojoules per mole of energy are required to remove potassium ions from iodide ions. And for potassium fluoride, the lattice energy is up to 808. It's considerably higher. Why? Well, they both have potassium ions, so we can ignore that. But let's look at the counter ion. Let's look at the iodide ion and the fluoride ion. Now, their charges are both 1 negative, but what about their radius? Let's take a look. Well, here is the potassium ion. Here is the iodide ion, right? It would gain 1 electron to become like xenon. And here is fluoride. It would gain 1 electron to become like neon. Doesn't iodine have 1, 2, 3, 4, 5 energy levels for its valence electron? Yeah. The fluoride ion has 1, 2 energy levels. Isn't it a much smaller ion than the iodide ion? So do you understand now why Kf would have the higher lattice energy than Ki? Kf would have a higher melting and boiling point. Okay? All right, let's look at the next one I want to show you. Let's look at rubidium fluoride now, with its lattice energy of 774 kilojoules per mole, and sodium fluoride. Its lattice energy is 910. Now we're going to ignore the negative ions here. They're both fluoride, so they both have the same charge, -1, and the same radius. They're both fluoride ions. But let's look at the counter ion here of rubidium and sodium, and let's see where that plays a role. So, here's the sodium ion, here's the rubidium ion. Okay, doesn't sodium have 2 fewer energy levels than does the rubidium ion? Now they're both bonded to fluoride, aren't they? But since sodium is the smaller of the two ions bonded to fluoride, it will have the higher lattice energy. And sure enough, it does. Okay, let's take a look at this. This is sort of interesting. Let's take a look at sodium bromide and strontium chloride. We have a couple of things going on here. Sodium bromide's lattice energy, 732. Strontium chloride's is 2142. Why is that so much higher? Well, let's look at the positive ions first, okay? Let's look at sodium and strontium. Okay, let's clear this so we can see it a bit better. So here's sodium and here's strontium. What do you notice right away? Well, you're right, sodium does have fewer energy levels, doesn't it? Strontium has more. But isn't strontium 2 positive, where sodium is only 1 positive? Now let's look and see what they're bonded to. We have bromide and chloride. See where they are in the periodic table. Bromide and chloride. Isn't the bromide ion going to be larger than the chloride ion? Yeah, so we would expect strontium chloride, because strontium's 2+ and has the smaller ion, to have a higher lattice energy than sodium bromide. Now I agree that sodium is smaller, but it only has a 1 positive charge, and it's bonded to a much larger ion. Okay? All right, now it's your turn. Why don't you decide on example 15 which of these pairs, cesium chloride or potassium chloride, has the higher lattice energy, and then do the same thing for potassium oxide and calcium oxide. So pause the video, circle your choice, and then come back to the video and see how you did. Alrighty, welcome back. So here we go. Cesium chloride or potassium chloride. They both have the same negative ion, so we're going to ignore that. So we're going to look at the size and charge of the positive ion. Okay, cesium or potassium. So let's go back to our periodic tables. Let's clear this mess off here. And we have cesium and potassium. Okay, it looks like they're both +1, so we can ignore the charge. However, doesn't potassium have 2 fewer energy levels? It's the smaller ion. Yeah, so my choice would be potassium chloride would have the higher lattice energy, therefore would have the higher melting and higher boiling points. Okay, next one. Potassium oxide or calcium oxide. So they're both bonded to oxygen. Okay, they're both the same radius as far as the negative ion is concerned in charge, but potassium versus calcium. So let's take a look at those on the periodic table. All right, potassium versus calcium. So potassium's +1, calcium is +2, plus isn't the calcium ion going to be smaller? So not only does it have a +2 charge, but it also has the smaller radius than potassium, doesn't it? So I would choose calcium oxide having the higher lattice energy. Therefore, it would have the higher melting point and the higher boiling point. Okay? All right, now when we come back with our next video, we are going to talk about covalent compounds. We're going to learn how to name and write formulas for them. Remember, we finished with ionic compounds. We're going to move on to covalent compounds next. So we'll see you soon. Bye-bye.